Hello all. Let's continue with our discussion on breakdown properties of a p-n junction diode. So last time we saw about thermal instability, tunneling breakdown, and today we will talk about an interesting breakdown and interesting and important breakdown, as well as it's called as avalanche breakdown or multiplication. This is an important phenomena in many of the devices, including a p-n junction diode, MOS transistor, tunnel diodes, and so on. Right. So we will deal this a little bit more in detail and see under what conditions it is more prominent, what are the currents, and so on. Right. So this is another phenomena once again under reverse bias. So what happens when we start increasing the reverse bias? You have the same p-n junction. Right. And the reverse bias, you have a much larger depletion width. Let us say the depletion width is WD, right? And you have a P on this side and N on this side. So you have an electron from the P, let us say, being injected into the p-n junction. Similarly, a hole from the N being injected from the N side, right? And let us say that if we can sustain a reverse bias current of current value I. Now, an electron or hole being present in the depletion width is actually accelerated by the electric field that is available, right? So the potential that it gets, the energy that it gets, is basically an integration of the electric field over the width. Right. That gives you the actual energy that the electron gets as it is being swept across in this junction. Right. So we can draw this schematically. So like we have, let us say, an n-type semiconductor here and the p-type here at very high reverse bias, right? So you have a lot of electrons here and holes. Right? If you are able to inject one such electron from the P side, it falls down through this huge potential slope. As it falls down, it excites more and more electron hole pairs on the way, thereby increasing the number as it goes down. Right? The same thing can happen for a hole on this side. Hole goes up this huge potential drop, which goes and then increases its by number as it goes through this. Right? And if I draw the current density versus spatial distance in the depletion width, right? So let us say this is I'm going to extend the depletion width, right? And I am having a total constant current on the top. This is I, right? And at the edge of the hole, so basically I have a hole current which is very small here, right? And which gets accelerated as it goes through the depletion width, because this electron from the p type is actually getting accelerated through this, right? Similarly, the same thing can happen for the electron from the other side. So you will have something like this. So this will be let us say IP naught before it enters into the depletion width, and this is IN naught. It all reaches, let us say this is 0 and this is the depletion width. It reaches to the maximum value of I at the end of the depletion width, right? And let us take at any point X within the depletion width, and the whole current is taken as IP of X, right? And in any small change in this position, let us say dx, we can write the change in the current or the increase in this current is written as dIP of X is basically the current IP, right? This current is the number of holes which are being injected from the electron side, right? So IP into alpha P being ionization capability of the holes into dx. So IP alpha p is the number of holes which are present per unit time in the depletion width, and it is the probability of the number of holes in the depletion width to ionize further carriers. So this is the additional electron hole pair that you generated. This is still the number of holes. Remember, the electrons also will create the same number of hole pair, right? So basically you will get In alpha n dx, right? So basically the holes create additional holes. Similarly, electrons will create additional electrons, right? You can write the same thing for electrons as well. The electron current will create additional electrons, plus the hole current will create additional electrons as well, right? Because each of these electron or hole will create an electron hole pair, both of them contributing to the electrons, right? This is what causes this avalanche multiplication as it falls down this big potential hill that we just now spoke about, right? So now let us take just one equation and then try to understand what is the actual current from this particular thing, right? So we saw that the total current is constant. So basically I is equal to In of x plus IP of x. At any point in depletion with the total current is going to be constant everywhere. So I can always write this In of x is I minus IP. So in this equation, dIP of x is IP alpha p dx plus I minus IP of x alpha n dx, right? So now I can write d by dx of IP of x minus alpha p minus alpha n IP of x is equal to alpha n, right? So basically this is a very known form of equation. Basically you have a y dash plus py equal to q kind of an equation, and you know what is the solution for this. The solution for this is basically IP of x is 1 by e power minus integral alpha p minus alpha n dx 0 to x integral 0 to x alpha n of I into e power integral 0 to x minus of alpha p minus alpha n dx dash. See, this is a general solution for a first order equation of this particular form. You must have seen this previously in your mathematical courses, right? So this is the solution for the whole current in the depletion width at any point x from the edge of the depletion width, right? You have two boundary conditions. You know this IP of x is equal to 0 is IP naught. We saw this particular point, right? And we know this IP of the entire depletion width is basically I, right? The total current is anyway constant, so your thing will go from here to here. And what we are trying to see is the whole current got to be multiplied from IP naught to I. So we call this by some multiplication constant I. This is the avalanche multiplication, right? This is basically I by IP naught. It is the actual multiplication of the whole current at the edge of the depletion width to the final current that we can obtain, right? This is the current that we're talking about. Just to give you some background, so in the reverse bias IV characteristics, you know this, you have a very small current for large values, and suddenly the current starts to increase, right? It is this current that we're talking about. That is the avalanche current that we're talking about at these conditions, right? We are talking about what actually causes this avalanche and what is its dependence and so on. So it is this M multiplication, that's what we want to find, under what conditions this multiplication happens, right? So now let me substitute these boundary conditions into this. I can easily see that C will turn out to be IP naught, right? If I substitute 0, and if I substitute x is equal to WD, So I will get IP of WD. IP of WD is basically I, right? And for the substitutions will give me that the multiplication constant m will turn out to be 1 by 1 minus integral 0 to WD alpha p e power minus integral 0 to x alpha p minus alpha n dx dash dx. So this will be the solution. So let us say if I substitute this thing here, the multiplication will turn out to be of this particular form, and we are trying to see at what point this multiplication is a very large number, and you can easily see that it will become a very large number if the denominator goes to 0 or it goes close to 1, right? So the actual condition for avalanche breakdown to happen is basically integral 0 to WD alpha p e power minus 0 to x alpha p minus alpha n dx dash. Remember, this alpha p and alpha n are ionization capabilities of holes and electrons respectively, right? And they are all dependent on the position, right? Because you are here at any point in the depletion width, at any point the velocity of these electrons and holes are very different, right? And hence the ionization potential alpha n and alpha p is going to be position dependent, and that's why we are not able to reduce this particular thing much easily. However, this is going to be 1. This is the condition for the same thing can be written for electron as well. 0 to WD alpha n e power minus 0 to x alpha n minus alpha p dx dash dx is equal to 1. You can easily see that the electrons and holes have a very similar behavior in the sense of its ionization capabilities, right? And hence it really does not matter what is the primary carrier of the current. It only matters is what is the field which ionizes this particular is a field which accelerates these carriers, right? So it does not really distinguish between the ionization being caused either by electron or hole or by a mixture of any of these things. And hence if we assume that alpha n of x is equal to alpha p of x, right, to some value, you can see that the condition for ionization can be reduced significantly to WD alpha p r n dx is equal to 1. So this is the famous ionization requirement which causes this knee in the reverse bias IV characteristics, right? Now to find the actual potential which is required to ionize, or it is the potential is required to cause this breakdown, you can easily see in our normal PN junction diode. Let us say that you have the junction depleted, and you know the electric field, the maximum electric field EM. Remember, it is the electric field which gives the charge just the acceleration. It is the electric field which actually causes the increase in the velocity as it actually traverses the depletion width, right? And if this is the depletion width which causes breakdown, I'm going to call it WDM maximum or something of the sort, EM being the maximum electric field. The potential which is required to break down, call it V breakdown, is basically an integration of this triangle, right? I'm going to, it is just this area under this triangle, and which will turn out to be EM WDM by 2. Okay. So this is the breakdown potential which is required. This is potential which is required to trigger the avalanche breakdown. And from our previous treatment, we also know that the width of the depletion width can be written in a simplified form, again as a function of the maximum electric field, is written as again EM epsilon s by 2q n, which is basically EM square, epsilon s being the electric constant, 2q n. So basically the breakdown potential depends on the maximum electric field, depends upon the dielectric constant, as well as on the doping density N. Right? With regards to the maximum electric field, you know this, that maximum electric field can be represented by root 2q Na or Nd, right? V bias, V reverse bias by epsilon s. Epsilon s being the dielectric constant. So basically this maximum electric field is a very weak function of the doping density, because you know the square root 2 dependence turns out to be like this, right? So after a particular doping density, the electric field does not change majorly with doping density. So electric field can be almost assumed to be constant after a certain doping field, and hence electric field depends mostly on the reverse bias potential. And you can see that from this a very small change in the reverse bias potential, because it is in square, you can easily see that any small change in the maximum electric field, you can see that the avalanche breakdown is immediately triggered. And also, as well as that, if the doping density N is reduced, right, you can the breakdown potential is higher. If I plot the breakdown potential at various doping densities for different semiconductors, it will look like this. Here I have impurity concentration N as I have plotted, and the breakdown potential, let's say VBR. It's all again a log plot, right? So you will have curves which look like this. As the doping density, the topmost one being for gallium phosphide, this is for gallium arsenide, and this is for silicon. You have materials with increasing band gap like this, right? So you can see that as the band gap is increased, the dielectric constant also increases, right? And hence the breakdown potential also increases. So it can also be seen in a physical fashion that you need larger and larger energy to actually create an electron hole pair if you have a larger band gap material, right? And that is why larger band gap materials have a much higher dielectric breakdown than smaller band gap materials. It also has to do with the dielectric constant, which comes in this particular way, in which the electric field is also being modulated, right? So basically the force that acts on a charge is inversely proportional to dielectric constant, right? So it comes from the other way around as well, but then let us just stick to the most simplest explanation, which says that to ionize or to create an electron hole pair, we just need that much energy equal to the band gap to create an electron hole pair. So the electron should be accelerated to a much higher potential with a much higher breakdown potential to actually create the ionization. But with respect to the doping density N, you can see that as you increase the doping density, the breakdown potential drops. So you can see that even a smaller and smaller width is now enough to actually ionize the carriers, and hence a highly doped semiconductor can be broken down much quicker than a lightly doped semiconductor. But then this is not true everywhere, because after a certain doping density, as we have previously seen, the tunneling current starts to take over. So before a particular doping density, you can have very high avalanche condition, and after a particular doping density, the tunneling current takes over. It can be seen here in our schematic as well, right? So basically you need an additional carrier here to fall down this potential, right? The more the potential that you take, you can see that you start getting more and more vacant states, permitting you to have tunneling contributions, which becomes more significant than the avalanche breakdown conditions, which happens when you have carriers and the conduction band even under such high reverse bias potentials. It's right. So to summarize, you have an avalanche breakdown, it depends, it decreases with increased doping density. Two, it increases with band gap, in the sense that materials with higher band gap has a higher breakdown potential. And three, what does temperature do? Can we estimate? Basically, higher temperatures will give you more and more phonon contributions. So an electron which is being accelerated gets scattered much more. So the mean free path now drastically reduces, right? So at higher temperatures, the electron do not reach to enough potentials, do not reach to enough velocities to actually ionize an electron hole pair. Therefore, increasing temperature increases breakdown voltage. Right? So till now we have spoken about breakdown in an ideal abrupt junction, right? We have taken examples of abrupt junction. However, there can be practical scenarios where you do not have this real nice abrupt junctions, right? So you might have situations where you have a silicon with silicon dioxide gap, right? And let us say that if we have, let us take that we have a n-type semiconductor, n-type silicon, and then you dope it P just under the under an opening in the mask. This is silicon dioxide, this is silicon, right? So you have a PN junction like this, and the depletion happens such that the applied potential, let us take, I have something like this, the applied field is straight here, right? So your depletion width is not uniform, but whereas like this, which is wider here but thinner here, right? So what happens under such situations is that you do not have a breakdown potential corresponding to the width which is here, and this is what we have calculated right now, whereas you will have a breakdown which is much sooner than what was expected, what was actually calculated, right? Because you will have a breakdown through these regions which is much smaller than the actual calculation of the depletion width that we have done right now. We will see this non-idealities in situations in MOS transistors when you have drain junction reverse biasing and stuff. We will deal with this when we get there, right? This is one example where avalanche breakdown is important. Another